This is Lesson 1.8, Solving One-Step Equations. In this lesson, you're going to learn how to combine constants in an equation with inverse of addition or subtraction. You'll also learn how to isolate a variable from its coefficient with the inverse of multiplication or division. Before we begin, let's review the concept of combining like terms in an expression. Here I have a constant, a number, like the number 1. It represents a value something that you know, that doesn't change. So we have a cube to represent our constant of the number 1. A variable is an amount or quantity that we don't know. Let's use a bag to represent our variable. We don't know what's inside the bag, we just know we have a bag. So in your expression of x plus 1 plus x plus 2, we can represent that expression with the pictures of a bag and a block and a bag and 2 blocks. When we combine our like terms, we're combining our variable terms together and our constants together. So it's like putting the 2 bags together, our variable terms, so that would be 2 x's or 2 bags. Plus, and we combine our constants together, 3 blocks. Let's continue practicing combining like terms in an expression. First, identify your variable terms with a circle. Remember that a variable term has a variable, a letter, and a coefficient, a number that's in front of it. And remember that all coefficients have signs, either plus or minus signs. We know when we have a term whenever we see a plus or a minus sign. So let me get out my pen and let's do this. Circle the variable terms. There is one variable term, and there's another variable term. What I don't want you to do is this, circling just the variable and not including the sign that's with it. Then identify your constant terms. Your constants, again, are numbers that do not contain a variable. And don't forget the signs that go with them. Once you've identified your variable terms and your constants, you can combine them. Combine your variable terms together by using the rules of adding integers, or SOB. So we have the variable term of negative 3k and the other variable term of positive k. Now when you use your rules of adding integers, what you are adding or combining together are your coefficients, the numbers that are in front of the variables. Well, negative 3, I can see that coefficient, but what's the coefficient of k? Remember, if you do not see the coefficient, it is 1, and the sign that goes with it, so in this case it's positive 1. Alright, let's use our rules of adding integers to combine negative 3 and positive 1. Negative 3 and positive 1 are opposite signs, so we have to subtract because it's same signs add, opposite signs subtract, and bigger sign wins. So we should get 3 minus 1 is 2, and the bigger sign is negative, so it's a negative 2, and our variable stays the same. Combining like terms is like a family. You can only combine them if they have the same last name, in this case the last name of K, and when you combine them, you combine it's like the parents of negative 3 and positive 1, their child is negative 2. Then we need to combine any constants. Well, in this case, the only constant in our expression is the 1. What's the sign of that one? Remember, if it's the leading term, if you don't see a sign, you assume the sign is positive. So when we're trying to combine our like terms and rewrite the new expression, we need to make sure we write plus 1. And again, remember, we have to write the sign of any term after the leading term, because the plus 1 or positive 1 is the second term in our combined expression. We have to write the sign regardless if it's positive. Look at your second example. Go ahead and circle your variable terms and then put squares around your constants. If you need some time, push pause while you do this and then push play when you're ready to check. Okay, let's see how you did. Did you circle the x term? Did you put a square around the positive 6? And did you include the positive sign with the 6? And then did you put a square around your positive 6? And then a circle around the negative x, including that negative sign. Alright, if you've identified all your terms correctly, now you're ready to combine. We always combine your variable terms before your constant terms. So we combine the variable term of positive x and negative x. And we said before the coefficients are 1, but notice you have a positive 1 and a negative 1. Do you remember what that's called? It's a zero pair. They cancel out. They equal 0. So now we just have our constants to combine. We have a positive 6 and a positive 6. Careful, do not cross those off. Those are not zero pairs. Just because they're the same number doesn't make them a zero pair. They must also have opposite signs. So that's a common mistake I see with students. Positive 6 and positive 6, they're same sign, so you add, which equals 12, and the bigger sign wins, which means it stays positive. So that all combines together and you get the answer of 12. It doesn't happen always, but occasionally you will have just one single number answer. But remember, usually when you're combining like terms in expression, you're still going to have an expression when you're left over, not a single term or a single number. Let's do your last example again. Identify your terms with circles and squares. Here you should have a variable term, a constant term, and a variable term. Then you're ready to combine your like terms. We have two variable terms that we can combine, so we need to use the rules of integers of same signs add. In this case, they're opposite signs, so we have to subtract. 9 minus 2 is 7, but the bigger sign wins. 9's bigger, so its sign wins the sign war. Keep its last name of y. Then we need to combine our constant terms. We only have one constant in this expression, so you just copy it down. But don't forget the sign because it's not the leading term in the expression. So I have a new word for you, the word isolate. In algebra, isolate is something that you do to a variable in order to find out what its value is. To isolate a variable in an equation means you get the variable with a coefficient of 1 alone on one side of the equation. Let's make sure you can identify an equation where the variable is isolated. Look below. Our first equation, you see 4x plus 1 equals 13. Is the variable isolated here? No, look, beside it has a 4 that's beside the variable, and also there's a 1 that's being added to the variable. So our variable is not all by itself, therefore it's not isolated. In the second equation, x is equal to 12 minus 7. If you look where the variable is, on the left-hand side of the equation, there's nothing else with it. It may have the coefficient of 1, but that's fine. The variable is considered isolated because it's on one side of the equation all by itself. In the next example, you have the equation x over 3 is equal to 10, or x divided by 3 is equal to 10. It can be both read the same way. Is your variable isolated? No. Look, it's being divided by 3. It's on the same side, so therefore this equation, the variable is not isolated. In the last example, 2 divided by 5, or 2/5, is equal to x. Here x is on the right-hand side, which is fine, as long as it's isolated or all by itself, which it is. So this equation is isolated. Until a variable is isolated with the known value on the other side, you won't know its weight. If you're thinking of a scale, you see on the scale how we have our variable on the left and some blocks on the right. We know how much the blocks are. They're 1 each. So in this case, our variable x is equal to 3. We know its value. But even if you don't know the value of a variable because it's not isolated, An equation must always remain balanced. Here we have the equation of x plus 2, the bag and 2 blocks, is equal to 5, or the 5 blocks. Notice our scales are level or balanced. But how will we isolate our variable so that we can figure out its value? Well, you see 2 blocks are with our bag right here, our variable. What are you going to do? Well, you probably say you're going to take them away, which you're almost there. Yes, if we took those 2 blocks off that side, but look what happens to our scale. It tips. The scale isn't balanced, so our equation isn't balanced yet. You wouldn't just add those 2 blocks to the other side on the balance. It still stays unbalanced. So in algebra, we have this golden rule. Whatever you do to one side of an equation, you have to do the exact same thing to the other side. So back to our problem of x plus 2 equals 5. Yes, we want to remove the 2 blocks on the left, but then we also, to keep it balanced, need to move 2 blocks from the right. Now our variable is isolated, and we know its value. X is equal to 3. Let's review again what it means to create a zero pair. A pair of numbers with a positive and negative sign whose sum is equal to 0. So here's some examples of a zero pair. Negative 9 plus 9 is equal to 0. They're the same number but opposite signs. So a couple more examples. 15 plus negative 15 equals 0. We can even have variable terms that create zero pairs. Negative 2x plus 2x is equal to 0. In this equation, x minus 2 is equal to 3. Someone has taken 2 blocks out of the bag, which now weighs 3. But if we want to know how many were in the bag at the beginning, and that's our variable, then what would we have to do? You need to always create a zero pair with negative constants. So that x minus 2, if we want to get x all by itself, how could we make a zero pair with a negative 2? Well, we'd have to add 2. So we're adding the 2 back into the bag. But we need to remember our golden rule. Whatever we do to one side, we must do to the other. So we're going to add 2 to the other side of the equation as well. By doing this, we created our zero pair. So we're going to draw a big fat line, and now we're ready to combine. We had that like terms of 3 and positive 2, and we use our rules of adding integers here. We had the zero pair on the left-hand side, so that cancels out. On the right-hand side, you have a 3 and a positive 2. Those are the same signs, so you have to add. Therefore, our value of x is equal to 5. A variable can only be isolated from constants with the inverse of either addition or subtraction. Then they can be combined with like terms on the other side. So here are 3 examples. The first example says to solve for x. The equation reads x plus 7 equals 4. To isolate the x from the constant of 7, here you have your constant, and here we have a constant, and there's the variable, but we want it, sorry, that's a little sloppy there. Let me try that all over again. So I'm going to identify my terms. I've got a variable term, a constant, and a constant. Right now there's the constant of positive 7 that's with my variable term, and I don't want it to be there. I want that variable to be isolated all by itself. So just like our scale, if there's 7 on one side, we need to take it away from that side. But we use our golden rule of algebra. Whatever we do to one side, we must do the other. We subtract 7 from the other side. Then we draw our big fat line and combine. Well, when we combine the positive 7 and the negative 7, that created that zero pair. So x is therefore equal to, and we have to combine or use our rules of adding integers, SOB, the positive 4 and the negative 7. So you have a positive and a negative. Those are opposite signs, so you have to subtract. 7 minus 4 is 3, but the bigger sign wins. The 7 is bigger than 4, so your final answer is negative 3. Let's try example 2. Here you have negative 10 plus x is equal to 12. Again, I'd start off by identifying my terms. Where are my constant terms and where are my variable terms? Here I have a constant of negative 10. Here you have a variable term of positive x and a constant of 12. Now this is really important to identify your terms before you begin. These are sort of like your training wheels. When you're first learning to ride a bike, you have those training wheels. Just like when you're first learning how to solve equations, we have a training wheels. We're going to use our circles and our squares. This is important so that we get our eyes used to looking and identifying the terms. I want you to be careful, and this is the reason why. I don't want you to do things like, oh, this. Even if I did a circle. But you got to be careful you don't do things like this, because then you'll be doing it all wrong. Like you won't know what to do with that 10, or you might mistakenly do the wrong operation. So let me try this again. We have a negative 10, a positive x, and a positive 12. Well, we have some like terms, those constants, the negative 10 and the positive 12. But that right now they're on opposite sides of the scale from one another. To get rid of this negative 10, I need to create a zero pair, a positive 10. And I chose the 10 and not the 12 because my goal is to get that variable all by itself. So it doesn't make sense to move the 12 over. I use that golden rule of algebra. Whatever I do to one side, I have to do to the other. Then I draw my big fat line and I'm ready to combine. Combining my like terms, I created the zero pair. That allowed me to get x all by itself is equal to, and then we combine our two constants. We have a positive 12 and a positive 10. That means we have to add them together to equal 22. And the bigger sign wins, so it stays positive. So there's your final answer. X is equal to 22. Look at your third example. 3 is equal to 4 plus x. Now some of you might be looking in there like, wait a minute, this looks different. It really isn't, but let's take a look at the picture of what this is representing. Remember that your goal is to isolate the variable. It doesn't make sense for us to move the constants on the left, that 3, to the right-hand side because it will not isolate the variable. Let me show you. If we take away the 3 from both sides of the equation, and then we combine our terms together, yes, we created a zero pair on the left-hand side, but on the right-hand side, the 4 minus 3 equals 1. So we have 0 equals 1 plus x. Our variable isn't isolated. Yes, we have a balanced equation, but we haven't solved the problem yet. So be careful when you choose which constants to move or remove, that you remove the ones that are on the same side of the equation as your variable. So here's that third example again. 3 is equal to 4 plus x. What term are we trying to remove? The 4, because it's with our variable. We don't want it with our variable. And to get rid of that 4, I'm going to give you a little rhyme to help you remember what you do. So if you ever see this little symbol of the brain in any of my notes, it just means it's a memorization technique. When you're combining your like terms, in this case constants, if you cross the lines, aka the equal sign, then you change the sign. So the 4 is what we're trying to move to the other side of the equation. So we would have to subtract 4 from both sides of the equation. We had to change the sign because we crossed the lines. So then you draw your big fat line and combine. The positive 4 and the negative 4 created that zero pair. That was the whole point, to get our x isolated. So our x is left on the right-hand side of the equation, and then on the left-hand side, we combine the like terms of 3 and negative 4. And that equals negative 1. But look at your answer. This is an answer, by the way. Negative 1 is equal to x. We know it's an answer because our variable is isolated, and the only coefficient it has is of 1. So yes, this is an answer, but it's also not what we call standard answer form. If we were wanting to write this in standard form, you maybe would be more used to seeing x is equal to negative 1. Both are really saying the exact same thing. It would be like saying, instead of negative 1 equals x, it'd be like saying, Stacy is my name. Well, that's my name, so I said it correctly, but I'm just not used to saying it that way. Instead, you will hear people say, my name is Stacy. Okay? So once you get your variable isolated with only one value on the other side, you may turn your equation around to write it in standard form. X is equal to negative 1. Isolating variables from coefficients are a little bit different. Remember that a coefficient is a number that multiplies or divides a variable. In the examples below, circle the variable term in each of the equations. So in example 1, you see the variable of x, but a variable term has a coefficient with it. What's the coefficient of that x? Well, I see a negative sign, but negative what? Negative 1. There's that invisible 1. If you don't see a coefficient in front of a variable, remember that it is 1. But coefficients always have signs to them. In this case, that negative went with that 1. So let's circle that variable term. In example 2, we have x over 4 is equal to 3. Our x is being divided by 4. Therefore, 4 is a coefficient. So the variable term is x divided by 4. We circle the whole thing. In the third example, 6 is equal to 2x over 3. So we have a 2 beside our x, which means multiply, and a 3 that's under, which means divide. So therefore, the whole thing is your variable term. So the key with isolating variables from its coefficient is you have to use the inverse of multiplication or division to isolate the variable from its coefficient. So in our first example, what is the operation of the coefficient? There you see a negative 1 that's beside our x. A coefficient beside a variable means multiplication. That's like saying negative 1 times x. The inverse is just the opposite. So what's the inverse operation of multiplication? Division. So in order to isolate this variable of x from its coefficient of negative 1, I would have to divide it by negative 1. Notice though that the sign of the coefficient does not change. The constants, when we were combining like terms, yes, those change. When you cross the line, you change the sign, but not with coefficients. Regardless if you're multiplying or dividing, whatever the sign of the coefficient, you will multiply or divide that number with its sign. The whole point of that is whenever you have the same number with the same sign on the top and the bottom of a fraction, it will always cancel out. After it's canceled, then our variable is all by itself. But we do have to apply the golden rule. Whatever we do to one side, because we divided by 1 on one side, we must also do to the other side of the equation. So we divide by 1 on the other side as well. After that, you have to use your rules of multiplying or dividing integers. Remember, this is not SOB. We gave you many different techniques to remember multiplying and dividing integers. Here I gave you the sine triangle again. Let me just remind you how that works. You have a positive 4, so you cover up a positive sign, over a negative 1, so we cover up a negative. Therefore, our final answer has to be negative. So you have x is equal to -4, because 4 divided by 1 is 4. Be careful with that. I can't tell you how many people put 1 for that. So again, I have another memorization technique. Everybody seems to love this one. If it's beside it, you divide it. So if you see a coefficient or any number that's directly beside a variable, you will always divide it. Beside it, divide it. It rhymes. So look at example 2. What is the operation of this coefficient? Well, the coefficient is 4 and it's under our variable. So the operation is division, because whenever you have a fraction bar, the number underneath is just saying it's being divided by x divided by 4. The inverse of division then is multiplication. So what you will do is multiply that x over 4 by 4. This will cancel out because you'll have one number, you'll have the same number, one that's up high and one that's down low of the fraction, that will cancel out. But we have to apply the golden rule. Whatever we do to one side of the equation, in this case we multiply by 4, we have to do to the other side. Then you use the rules of multiplying and dividing integers. So our x is all by itself, and 3 times 4 is equal to 12. So of course, I've given you a rule or a memorization technique. If it's under, you move it up and multiply. You can just say under, up, and multiply. Because what we did there is we had that 4, and we moved it up and multiplied. And then we move that up and multiply to both sides of the equation. So in example 3, 6 is equal to 2x over 3. What are the operations of the coefficient? Well, we have an x with a 2 beside it and a 3 under it, so we have both operations being applied here. The 2 is being multiplied to x, and the 3 is dividing the 2 and the x. To always perform inverse multiplication before you apply inverse of division to isolate a variable. So what we mean by that is the first thing you have to do is under, up, and multiply. So we're going to multiply both sides by 3 because our denominator, or the number that was underneath our x, was 3, so we multiply both sides of the equation by 3. That cancels out the 3's. And then we use the rules of integers. 3 times 6 is 18 is equal to 2x. The 2x still remains. Then you beside it divide it. So under, up, and multiply, then beside it divide it. So we're going to divide both sides by 2 because that's the number that's beside our variable. The 2's then cancel out because we have one that's above a fraction bar and one that's below. 18 divided by 2 is 9, is on the left, and then our x just comes down on the right. So we have 9 is equal to x. Or you can rewrite it in standard form of x is equal to 9. Sorry, get a question here. To check an answer, you can do so by evaluating the number. So here I have a problem. Is 6 a solution to the following equation? Let's say you did all your work, decided to divide it, under, up, multiply, or cross the lines and change the signs, whichever rules you applied, and you get a value for your x. Okay, in this case 6. We want to know, is 6 the correct answer to the equation? What you will do is evaluate the expressions on both sides, or just rewrite the entire equation, but wherever you see a variable, notice I put a set of parentheses. That's sort of like a little hole or a placeholder. So I rewrite it with our hole. Whatever answer that you get when you solve the problem, you plug it into that hole. Whoops, sorry, my thing's in the wrong order here. Okay, let me try that again. So you had 7x equals 42. You recopy the equation, but you leave that hole. The value that you solved for, you plug into that hole. and then you evaluate each side of the equation separately. So just looking at the left-hand side of the equation, we have 7 times 6. Because there's no variable, now we can use our order of operations here. And there's nothing inside our parentheses. The 7 next to the 6 in parentheses actually means multiplication. 7 times 6 is 42. So does that equal 42? Yes, it does. So the solution checks. Well, what if you got 8 as the solution to the same equation? Let's try that. Again, I will copy down the problem, or the equation, the original equation, but wherever I see a variable, I'm going to put a set of parentheses to be a hole or placeholder for my value. I want to know if 8 is a solution, so I'm going to plug in that 8 inside the hole there. Well, what's 7 times 8? It's 56. Does 56 equal 42? No, it does not. So the answer of 8 is not a solution. The few minutes extra that it would take for you to plug in your answers into the equation to check your answer is worth your time. Few minutes of checking to make sure that each one of your answers are correct will guarantee that you pass the class versus retaking a full 8 weeks because you just simply wanted to take the extra few minutes to check your answers. On the ECA exam, with any extra time that you have, please, please, please go back and check all of your answers by plugging them back into the original equation. Alright, let's practice a few of these before you do your guided practice. These types of equations that we are solving are called one-step equations. One step because you are either going to combine like terms or you're going to isolate a variable from its coefficient. When I say combine like terms, we're combining our constants. So to solve each one of these problems, I would advise you to do these in about 4 steps. Now, one of these steps you're going to combine, or you're going to skip. You're either going to get to skip step 2 of combining like terms because there aren't like terms to combine, or you're going to skip step 3 because there aren't any variables to isolate. So, our first step, identify the types of terms. This will help you to determine what you're going to do next. So let's identify our terms. We have a variable term, a constant, and a constant. Now you're going to ask yourself, well, which of these 2 steps do I have to do next? Well, look, what do you have? Do you have any coefficients that you need to isolate? No. Do we have any constants that we need to combine? Yes. We have a constant of positive 3 and a constant of 11 that we need to combine together. But before we combine them, we need to get our variable, the x, all by itself. So what are you going to get rid of? The 3 or the 11? Did you say 3? And what would you have to do to get rid of the 3? Create a zero pair. So we're going to subtract 3 from both sides of the equation so that we have that zero pair and we follow the golden rule of whatever we do to one side, we have to do to the other. Then you combine, or draw your big fat line and combine your like terms. So x is equal to, and when you combine, you have to remember to use SOB. 11 and a negative 3 are opposite signs, so we have to subtract. 11 minus 3 is 8, and our bigger sign wins. So it stays a positive 8. We do not have any variables in front of our, or we don't have any coefficients in front of our variable except for 1. So we're done. Okay, there's only a coefficient of 1, then you're done. X is equal to 8, but let's check our answer. To check, remember, we write down the original equation, but wherever we see a variable, we put a set of parentheses to be a placeholder. Then you're going to plug in your answer of 8 into that spot. Evaluate just the one side of the equation and then the other. 8 plus 3 is equal to 11. On the right hand side, the only thing we have is 11, so we just copy it down, 11. Does 11 equal 11? Of course, so our answer checks. The answer to the equation is x is equal to 8, And we proved that the answer is definitely 8. Looking at the next problem. First thing, identify your terms. So let's circle our variable terms. We only have one. And put a square around any constant terms. In 81, we only have one. So we finished step 1. Step 2, we need to combine any like terms. Do we have any like terms to combine? No. So we get to skip that step. Step 3, isolate the variable from its coefficient. Yeah, we have a variable here and it's not by itself. We have a 9 that's beside it. So what do? If it's beside it, you divide it. Yay. So we divide both sides by 9. Beside it, divide it. The whole point of dividing by the 9 is that it cancels out the 9s, 9 over 9. So k is equal to, and 81 divided by 9 is 9. We have a positive divided by a positive, which equals still a positive. Yeah, they're both the same sign, so it stays positive. 9. All right, let's check, make sure we did get the right solution. So I'm going to copy down the original equation, 9 times k, but I don't write down k, I just put a set of parentheses to leave a hole, equals 81. I almost wrote 18. 81. Then I replace or plug in the 9 that I got from my solution, and multiply 9 times 9 equals 81. Does 81 equal to 81? Oops, I wrote 18 again there. 81. Yes, so the answer checks. Alright, you tried this one on your own. Push pause and see how far you can get, and then push play when you're ready to go. Alright, we're ready? By the way, as I'm showing you the answer, if you make a mistake anywhere, then please pause the video again, finish and correct your mistake, and try to rework the problem, and then push play to keep on checking. Alright, so my first step is identifying my terms. I've got a variable term, a constant, and a constant. Did you remember to put the negative with the 9 inside that constant? Alright, so I finished step 1. Now I need to combine any like terms. Do I have any like terms to combine? Yep, I have a negative 9 and a 4. See how those squares are kind of like our training wheels? They're training our eyes. Hey, we've got 2 squares we need to combine together. But right now they're not on the same side of the equation as one another. So we have to move the 9, the negative 9. And when we move it to their side, you need to make that 0 pair to move it. So we need to add 9. Follow the golden rule, add 9 to both sides. So we draw our big fat line and we're ready to combine. The 0 pair cancels out and we have y is equal to 9 plus 4 is 13. The bigger sign wins, so it stays positive 13. Then, did you check your work? Y, but instead of y I made a parentheses, minus 9 is equal to 4. It's the original equation, but instead of writing y, I made a set of parentheses. Then I'm going to plug in the 13 that I got for my solution and simplify the expression. 9 minus 13, or I'm sorry, 13 minus 9 is 4. And because 4 is equal to 4, check, I did it right. Alright, try example 4. Push pause and then push play when you're ready to check. Hopefully even in the last one when you plugged your answer in and checked it, if you made a mistake you were able to catch it before you even watched the video. Alright, are you ready to go? First things first, let's identify our terms. We have an x over 4. So that is a variable term. You circle the whole thing together. Is equal to 11. 11 is a constant because there's no variables with it at all. Do we have any like terms to combine? Nope, we got a variable term on one side and a constant on the other. Those aren't like terms, so we get to skip the step. Then we need to isolate our variable from its coefficient. Here we have a 4 that's under. What's the rhyme? Under, up, and multiply. So you multiply both sides of the equation by 4. The whole up thing is going to help you out, especially if that 11 was not just a whole number, if it was a fraction later. So do say that whole rhyme, under, up, and multiply. It'll make more sense later why I emphasize the up. The 4's cancel out. So x is equal to 11 times 4 is 44. And then you can check your work. Here I have that whole, or that placeholder where the x is over 4 is equal to 11. Now you're probably thinking, why does she keep on making a set of parentheses? Trust me, later on when we get some more complex equations, the parentheses are really going to make a difference. So we're going to replace inside the parentheses the 44 solution that we had before. So we have the number 44 divided by 4, which does reduce to 11. So does 11 equal 11? Of course it does. So you check. Alright, you're ready to begin your guided practices. Now remember that when you do these equations, you're going to have a mixture. Some of the one-step equations are going to be ones where you have to combine your constants together. So you have to combine like terms. In other equations, you're just going to be isolating your variable from its coefficient. Doing that first step of identifying your terms, like using the circles and squares, are really going to help you understand or know which step to apply. Good luck on those.